Okay, so I apologize for the delay that there was a sudden Wi-Fi issue at my home. So I need to actually rush to the campus and trying to get everything here. As I mentioned in the chat room that because I don't have any second screen anymore. So for today's lecture, if you have any question, feel free to interrupt me during the class using the microphone because I don't have the second screen. So it's very hard for me to monitor the chat for today. Okay, so if you have any question, just directly ask me using your microphone. If you really don't have microphone, then you can leave your question in the chat and I will go back to check it later on today. Okay, so because we delayed 10 minutes, so what I plan to do is the following. So I'm still going to cover the whole 75 minutes, meaning I will be 10 minutes late, like after the class. So I will still keep going on until 1:55. But if you have any classes or any obligation that you need to go, like feel free to just leave early. And since I'm going to record everything anyway, so then if you miss the last 10 minutes because it's over the class time, you can go back to watch the video later on. So because I think it's for the completeness, it's better for me just to do the whole 75 minutes. And so before we get started, just a quick announcement. So first of all, don't forget that homework 5 is due today by tonight. So I've seen a lot of people haven't submitted. So there's only a couple questions from 2.3 and 3.1. So it shouldn't be too bad. And so don't forget the homework 5. And I believe most of you already saw the announcement I sent out last night about the exam 1. So basically what happened is that the original total score was 65. So I want to give out 3 bonus points, meaning now the total score would be 62. So for example, if you get 52 out of 65, then now it will be 52 out of 62. Okay, so this is the how I'm going to do this. So then I announced all the average and median on the Blackboard, and also I mentioned that this exam should be a learning lesson that to a perfect chance for you to re-examine that how you study this subject. And so please take a look at the exam 1. That first make sure that the score is everything is correct. I double check, triple check, it should be fine. But mistake happens. So if you see any discrepancy of the total score, for example, please let me know. And you should be able to see your exam on the My Grade menu. And I returned the exam paper as an attachment. Okay, so then you're going to see, and for some of you, I actually left some message there. So you will also see my comments there. And once you click it, you will see your graded file. And if you have any questions about the exam, you can let me know by next week. And if you want to discuss with me about the exam 1 or about your performance or about how to study linear algebra in general, feel free to make an appointment with me. Okay, especially if you want to have a one-to-one private meeting, then definitely you have to make an appointment with me so we can chat on the Zoom one-to-one. And yeah, so basically also after you got your exam back, right, after you see it, please compare with my solution posted. You're going to see that most of the questions are actually pretty short if you use the right method. So a lot of time, of course, there's no right or wrong, but there's a more appropriate method in the sense that yeah, of course, there's so many methods that can make one problem work. But there's one method that takes 30 minutes, but there's also a method that only takes you 5 or 10 minutes. So you need to learn that how to do the most straightforward way. And so please take a look at my solution, then you will see what's the most, what's the method I'm thinking in mind when I designed this question. And as I said, if you have any question, feel free to stop by the office hour or make an appointment with me. And please double check. And especially if you feel like you didn't do well this time, definitely redo the exam problem. Once now you don't have the time limit, redo the problem, see whether you really have an issue with the material or you have an issue with the time, right? Trying to figure out that what's the obstacle here. And if you still feel uncomfortable about it, then please come to talk with me. Okay, so any questions so far? Questions? Okay, so what I'm going to do today is, so last time we started 3.2, which is about subspace. Okay, so basically once we know the subspace, there's a lot of nice space, which is our subspace. Okay, so last time we, in the very end of Tuesday, we introduced the so-called null space. So basically null space is the collection of all the vector x such that it satisfies AX equals 0. So you're essentially collecting all the solution to the homogeneous system. And as we know from the exam 1, that such homogeneous system always has a solution, right? So it's always consistent. So which means that essentially the trivial solution 0, 0, 0, 0 is always in the null space. But then essentially last time I actually proved that null space, we can check that it's a subspace of the domain. Okay, so today what we're going to see is to study more like nice type of subspace. And one important example is what we call the spanning set. But first we need to recall how to define a spanning set. So first of all, let's recall this definition. I kind of presented last time, but since it's really important, so I want to recall the definition here again. So first of all, let's say you have n vectors in a vector space, okay? And doesn't matter how many of them, right? Just some n vectors, okay? Then if you write a sum like this, some constant C1 times V1 plus C2 times V2 dot 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 till Cn times Vn. This is a new vector, right? If you want to call it V, whatever, right? This is a new vector. And if you have a vector in this summation format, consist of essentially kind of like consist or constructed from V1 to Vn in this format, then this is what we call linear combination of V1 to Vn. If you still remember the exam problem for B, essentially asks you to write a vector in terms of linear combination of some column vectors, right? So I hope the memory is still fresh here. Then we want to say, okay, what happened if we collect all the possible linear combination, right? If you give me some choices of the coefficient C1 to Cn, I give you a linear combination, right? I give you a vector from the come out from the linear combination. So you can actually have like different choices of the coefficient, right? Then you will have different vector. So the question is, okay, what if we collect all the possible linear combination like this, right? Then you essentially collect a bunch of different vectors. Then the set of all the possible linear combination of this n vector is what we call the span of V1 to Vn. And we use this notation span, the parenthesis of V1 to Vn means that it's the collection of all the possible linear combination out of this n vectors. As you can imagine, there's already infinite many vectors in this collection, right? Because you can see that you can free to choose what C1, C2, C3 to Cn is, right? So basically you can see that you can, so this collection is already have infinite many vectors in it. But it turns out that this collection form a nice structure or has a nice structure. This subset is actually itself a vector space, meaning it's a subspace. So this is I think I end at this theorem last time. So if you have n vector from a vector space, then the span of this n vector, meaning the collection of all the linear combination of these n vectors, it's going to be a subspace of this vector space, right? Because if you think about it, right, I didn't collect all the possible vectors in V, but instead I collect all the possible linear combination of V1 to Vn, right? So it's definitely a subset. It may be the whole V, but it may not be. That's why we know it's a subset of V, right? But we can actually prove, which I'm not going to spend too much time proving today. We can actually prove by using the definition of what the span is to show that this collection of all the linear combination is actually a subspace. So how do you check it? It's really just first check it's non-empty, which is definitely non-empty because any V1, V2 to Vn, any one of these vector is already in a span, right?
Hello?
And yeah. What's the question?
Can you hear me?
Hello? I heard something.
I can't hear you and
Oh, you cannot hear me? Oh. Give me a second. Let me check. So can anyone hear me now?
Yeah.
Okay. So yeah, so actually I want to also warn everyone, like I noticed actually just now, like an hour ago or almost 2 hours ago that I'm currently on campus, and I think the campus internet is also having some issue today, like all the network issue. So just to give one a heads up that if suddenly the internet go off, like you cannot hear me, let me know, like what you just did, like and if it really unfortunately that everything go off, that I cannot come back, then what I'm going to do is then I will just recording everything and then post it. Okay, so let's see how far like we can go today. Like for whatever reason, like everything is like having issue, including the university internet service. Yeah, I think the campus has some issue. That's why I don't know, like my home also has issues. So I was actually choosing between definitely an issue and possibly an issue. So I run to the campus, and hopefully this internet here can sustain me long enough. Yeah. So if you cannot hear, then maybe, I don't know, how come you cannot hear, but you can see me? Yeah, maybe did you, or maybe like the if you are using some speaker or something, like change the setting, see whether there's some problem with the setting, because sometimes if you switch the output of the voice, they might switch back and forth, or you can try to reconnect. Okay, so I just want to give everyone a heads up. If there's any tech issue, it's very possible that it's the campus internet for today. Okay, so let's continue. Okay, so first of all, let's see. So yeah, so this span of this, so essentially the collection of all the linear combination is a subspace. So it's definitely non-empty, as I just said. Then you can actually check. So that what remains to check, just check if you have, just check the closure, right? If you have a vector which looks like a linear combination, right? For example, which looks like linear combination of V1 to Vn, right? If you multiply by a scalar number, will this still be in span? As you can imagine, if you multiply this type of sum by a scalar number, it will still be in the format of linear combination, right? Because now it will just looks like alpha C1 V1 plus alpha C2 V2 plus alpha Cn Vn. So it's definitely another linear combination, right? So definitely alpha times any vector in the span will still be in the span. And you can do the same thing with addition, right? You pick random vector from the span, meaning this two vector looks like linear combination, maybe with different coefficients, but you add them up, then you just essentially add up those two coefficients. The new vector will still looks like a linear combination, so it will still be in a span. So the proof is actually quite straightforward. I think it's a very good exercise that people can do it as an exercise, or actually you can, if you can read the proof in the textbook. I think I believe they have the nice detailed proof there. But as I said, the proof is really not long at all. It's just 3 lines checking. Okay, so now the whole point is from now on, we want to understand algebraically and also geometrically what a span looks like. So let me use the kind of the easiest example, right? So let's just take R3, for example. And I'm going to take this spatial 3 vector. As you can see, this is the standard vector 1, 0, 0, 0, 1, 0, 0, 0, 1, right? So first, let's check what's the span of E1, E2 looks like, right? So you can see that, okay, span of E1, E2 means it's the collection of all the vector in this format, which looks like linear combination of E1 and E2, all possible linear combination, right? So then you can see that, okay, all possible linear combination, meaning I can free to choose any C1 and C2, right? So then if I just add them up, right, I really want to see that what's the vector looks like. So I really like just algebraic calculate C1, E1 plus C2, E2. And as you can see, I'm collecting all the possible vector, which looks like C1, C2, and 0, right? And C1, C2 can be any number. Now, if you think about it in R3, what type of vector will always looks like C1, C2, 0 for some C1 and C2? Then you can imagine it's any vector which lies on the XY plane, right? Because if you think of C1, C2 as X and Y, and you are free to choose what X and Y are, then it's really just the XY plane. So geometrically, the span of E1 and E2 really looks like just the XY plane, as I said, right? So if you put X, Y, and Z in R3, right, then E1 is here, right? And E2 is here, right? This is 1, 0, 0, and 0, 1, 0. Then the span of E1 and E2 will be essentially the floor, the XY plane, right? So the upshot is we can observe that span of E1, E2 is nothing else but the XY plane, or you can say X1, X2 plane, right? Or if you don't feel comfortable, you can think of its XY plane, right? And so basically this gives us an idea that, okay, it looks like that span of two such vector will be a plane, right? Because especially these two vector E1 and E2 does not align along the same line, okay? So then we have this nice observation. Now we think about, okay, what happened if we take the span of the whole E1, E2, and E3, right? If you think about it, if you take the span of all E1, E2, and E3, then that means if you do the calculation again, right, you put C1, E1 plus C2, E2 plus C3, E3, then you are essentially forming a vector which looks like C1, C2, and C3. That means it's any possible vector in R3, right? So then we actually know that if we take the span of all such three vectors, this is essentially the whole R3. So this is actually very nice in the sense that just taking the span of three vectors, right? Then, or in other words, you can say that any vector in R3 looks like a linear combination of E1, E2, and E3, which is kind of obvious, right? Because E1, E2, E3 has 1 in each coordinate, right? So if you have, say, a vector A, B, and C, right, then it always looks like A, E1 plus B, E2 plus C, E3. So this is actually not hard to see that the span of these three vector in particular is the whole R3. So now I want to continue this thought that, but what if I pick any random two vectors in, like for example, in R3, right? Then what would be the span looks like, right? Not necessarily E1 and E2, but some vector U and V, right? But here, in order to have a nice geometric picture, I want to actually restrict to a specific choices of U and V here. So I want to make sure that U and V can actually determine a parallelogram, right? You can see that in the previous example we just did here, E1 and E2 also can form a parallelogram, right? They're actually perpendicular to each other. So actually the parallelogram would be a rectangle, right? But here U and V may not necessarily be perpendicular, right? So for example, let's do X, Y, Y, Z again. But I can pick, for example, U to be here, right? And maybe V here. They are not necessarily perpendicular to each other, but some two vectors. But you can see that they can actually form a parallelogram, right? So if this is the case, right, later on we're going to see that the reason we require this is because we want to make sure the span is a two-dimensional plane. And the fact that it can actually form a parallelogram is what we call the linearly independent. But we haven't touched this topic, so I just want to assume this, and later on, once we reach section 3.3, 3.4, then it makes more sense now. So if U and V can form such a parallelogram, then the span is going to look like a two-dimensional plane, same as what we saw just now, right? So the span is a two-dimensional plane that contains this parallelogram. So if you look at the picture, so since U and V can form a parallelogram with no problem, then the span is going to be the plane passing through this parallelogram. Okay, so keep in mind when I say plane, it means infinite large, right? Extended to infinity. I cannot draw an infinite large picture now, but I'm trying to draw as big as possible, right? So it's the plane that containing the parallelogram formed by U and V. So you can see that if U and V has this nice property, then span of these two vectors will be two-dimension. And you can see that I'm going to say also later on mention what two-dimension means, but it's really the plane that we know usually, okay? So then this is the geometric picture we can have regarding the span, okay? So this is not too bad. I think it's quite intuitive, especially that if you start with, for example, the standard vector E1, E2, and E3, you can play around with it and see what will be the span looks like, okay? So essentially, you may argue with me that, oh, why the span of these two vectors looks like a plane? Because you can see that, okay, if I'm collecting all the vector, looks like linear combination of U and V. So you can see that U plus V will actually be here, right? So U plus V is this vector, right? Which is the diagonal of your parallelogram, right? So you can see that U plus V is one type of linear combination. It's 1 times U plus 1 times V, right? So basically you can see that all the possible linear combination will be on this plane, right? All type of linear combination, right? You might have, say, 2U minus 3V or 2.5U plus 3V, those type of thing, right? You collect all of them. That's why it will be the plane passing through that parallelogram, okay? So now we want to introduce this terminology. It's kind of the rephrase. So basically, we said that, okay, if we have m vectors, a set of m vectors, we say it's a spanning set for some vector space W if all the elements in W is formed by a linear combination of V1 to Vn. Or in other words, if all the elements W lies in the span of this M vector, then we say this M vectors is a spanning set. It's like a foundation, right? If I have some vector space and I know all the elements in this space looks like the linear combination of these M vectors, then I said this is the foundation. This M vector is my spanning set for the vector space W. But mathematically, you need to kind of react that what does that mean mathematically? It really means that for any vector, if you call it small w in this space, any vector W would be a linear combination of V1 to Vn for some choices of the coefficient C1 to Cn. Okay, so this is just the definition that, okay, if my vector in the vector space can be written as a linear combination of some set of vector, then I found my foundation. And this is what we call the spanning set. Okay, so now let's see how a lot of time, if you give me a set of vectors, maybe 3 or 4 or 5, doesn't matter. I want to see whether I can use all these, say, 3 vectors to span the whole space, right? So because if we know that any vectors in my vector space can be written as a span or as a linear combination of some vectors, then in some sense, I can, as long as I can control the spanning set, right? If I can control those V1 to Vn, then I know what's going on for the whole vector space, right? Because every vector in my space looks like linear combination of V1 to Vn. So instead of study infinite many vectors, I only need to know exactly what's going on with all this V1 to Vn. Then the rest of it is just a linear combination of these M vectors. That's why people were eager to know that, can I find my spanning set for some spaces, right? Or if you give me some set, that set going to be a spanning set. So let's take a look at this example here. So first question, I already tell you the answer. Show that this set of 3 vectors, that's called it V1, V2, and V3, is a spanning set for R3. Okay, so now the difficult question is to realize that what you want to solve. So from now on, you're going to see that starting from chapter 3, from now on, it's getting very conceptual in the sense that like you might know like some definition of certain things, but the difficult part is to turning into solving some mathematical problem. The first step is actually the most difficult. Once I tell you which equation or system to solve, then it becomes algebraic problem, but there's a gap between turning the concept into an algebra problem. So the idea is, okay, how am I going to show you that this 3 vector is the spanning set? Then to rephrase this question, we want to confirm or convince ourselves that is it true that any vector in this vector space, if you want to see coded W, right? Is any vector, arbitrary vector, A, B, and C in R3 can be written as a linear combination of these 3 vectors, right? This is essentially the rephrase of definition of being a spanning set, right? We want to use these 3 vectors to span the whole space R3. In other words, you're asking, is any arbitrary vector A, B, and C in R3 a linear combination of V1, V2, and V3 or not, right? And this has to be true for arbitrary vector, not just some, right? If we want to call V1, V2, V3 to be our spanning set, you need to make sure once you do the linear combination, you can always reach every single vector, right? So this has to be a general proof in this sense. Okay, so now let's see. So we already know we want to solve linear combination, right? So basically we turn this into an algebra problem. So we want to find x1, x2, x3 such that we want ABC to be able to be written as a linear combination of these 3 vectors. So x1 times v1 plus x2 times v2 plus x3 times v3, right? Okay, so we want to find this such that A, B, and C can always be solvable for this system, right? So now let's see. So we want this to be solvable. So we want this system to be solvable for any A, B, and C. Okay, it need to be any A, B, and C, right? If there's some choices of A, B, and C such that this is not solvable, then it's not a spanning set. So now I want to convince you, because I already tell you the conclusion that it's indeed a spanning set, right? So I want to actually convince you that this is always solvable from the algebra. Okay, so now let's see. So we want to see what system we are going to solve, right? So you can see that, okay, then once you rewrite everything, right, add up everything, you're actually solving this system. If you combine all the vector, right? If you combine all the vector here, you can see that this is essentially, we are solving this system, right? The usual 3x3 system that we know of. So now at this point, I'm asking, okay, is this system always solvable for any arbitrary A, B, and C? And your answer, of course, would depend on what A, B, and C are, right? Because it depends on the choices of A, B, and C. But as long as you can always solve it, then we are fine. At this point, there are actually several ways to solve this system. Of course, you can say, okay, then usually when we want to solve a system, we turn it into arithmetic matrix, right? So you can either solve it using arithmetic matrix, right? Then you will see that, okay, this would be something like this, right? Either solve this arithmetic matrix. Or if you prefer, you can keep the original system, because as you can see, this system is so easy. in the sense that in some sense, it's already in some type of triangular form, right? So actually, I already know that I specifically picked this system easy enough so you can kind of see the solution right away. So if you already notice that I already know what's the solution for x1 because x1 has to be C, right? So we already know that, I mean, either way, right? From either approach, either you stick with the original thing or you turn it into augmented matrix, whichever you want, you can already know that x1 equals C, right? And then if x1 equals C, then you can plug in back to the second equation, right? Then you can know that x2 will equal B minus x1, which means x2 has to be B minus C. Okay, so that's why I say your answer will depend on the choices of A, B, and C. Then do it again, right? Then we can plug in back to the first equation. Then I want to solve x3, right? So basically x3 will equal A minus x1 minus x2, yeah. And this will be A minus C minus B minus C, right? So let's solve it. So this will be A minus C minus B plus C. So this would be A minus B. Okay, so then what does that mean? So then it means that if you give me any arbitrary A, B, and C, arbitrary number A, B, and C, I can always rewrite this vector A, B, and C in terms of linear combination of those three vectors, 1, 1, 1, 1, 1, 0, and 1, 0, 0. And let me show you what's the conclusion. Let's double check, right? I already solved the coefficient x1, x2, x3. That's plugging back, right? So the upshot is, you can see A, B, and C is always, because now we solve the system. So it can always written as x1, right, which is C, times 1, 1, 1, plus x2, which is B minus C, times 1, 1, 0, plus x3, which is A minus B, times 1, 0, 0. And this is what you should check after your solution, right? So you can see that this is always true, right? Any arbitrary vector A, B, and C like this, it's definitely a linear combination of V1, V2, and V3, right? So basically, the conclusion is indeed any vector A, B, and C in my vector space, which is R3, lies in the span of these three vectors, which is, let me write down the three vectors here. Right? So that means, in other words, this three vector is my spanning set. Okay, so any question so far? This is a little bit abstract, but as you can see that it turns into a algebra problems. Any questions so far? Okay, so now I'm going to move to a slightly harder question, meaning the algebra is a little bit more involved. Okay, so for this type of spanning set, the only way to master this is really to like practice a lot of problems. So once you see like enough different type of question, then you know that what kind of situation means that it's not a spanning set, what kind of situation means it is. And even more, you're going to see that we are going to work through different type of vector space, more abstract one. Okay, so let me use another example in R3, right? So now the question I ask is, does these three vectors, let me call it U1, U2, and U3 this time. Does this three vectors span the whole R3? Now I didn't tell you the answer. I don't know yet for sure that whether any vector in R3 is going to be a linear combination of those three. Okay, I don't know, right? So now that we need to check. But as you can see, I'm essentially asking the same question as earlier, right? But now the only thing is that I don't know the answer. But the idea of solving it is the same. I'm still asking, if you give me any arbitrary vector A, B, and C, will it be able to be written or solved as a linear combination of these three vectors, U1, U2, and U3? So the question is the same, right? Can we solve C1 times U1 plus C2 times U2 plus C3 times U3 equals arbitrary A, B, and C. So same question, right? We want to see that if you give me arbitrary A, B, and C, is this system always solvable, right? And you can see that this is going to turn it into a 3x3 system, like what we saw, right? So this is the same as equivalent to solving the following system. So you're essentially, if you added up all the things together, if you already see how to turn it into a arithmetic matrix, then you can skip this middle step, that's fine. But I'm just also want to write it down as a for completion. So you're essentially solving this system. And your variable is now C1 and C2 and C3, right? If you're not comfortable, think of it as X1, X2, X3, okay? So now turning into arithmetic matrix, right? So you're essentially solving this arithmetic matrix. And as you can see that if you want to directly skip the middle step, that's fine, because you already observed that this is going to be your U1, U2, and U3, right? So this is U2. So you can see there's a pattern here. So we want to solve this system and see, is it this system always solvable for arbitrary A, B, and C? Okay, so now that's solved it. Now it becomes Gaussian elimination. That's why if you're not comfortable with Gaussian elimination from the first part, you need to be careful. Plus 3 in line 2. Let me see. So plus C2. 4, 3, 2C1 plus C2 minus C. What do you mean plus C? Let me see. What's the question? I see the question here. It should be plus C3 on line 2. No, it's actually minus 1 here, right? It's a minus 1 here, so it should be minus C3. Does that answer your question? Is that what you were asking? This line 2? Okay, so now, as I said, like it's very hard for me to monitor the chat room for now because I don't have a second screen, so I might delay your question. So okay, so now we want to solve this system, right? So now let's see, it really go back to the usual Gauss elimination. So we start from this, right? So I want to do eliminate 2 and 4. So I'm going to do take row 1 times minus 2 added to row 2. I do the same thing with the third row. Okay, so now let's see. Keep the first row. Okay, second row, you want to be careful, right? Because after you do that, you're going to get something like this. And don't forget, you need to change the right-hand side as well. In the exam 1, I've seen like few of you actually forgot to change the right-hand side, then there will be a problem. And same thing for the third row. So you're going to have something like this. Okay, it looks a little bit ugly because all these A, B, and C are like abstract, right? But you need to keep track of it. Okay, so now let's see. So at this point, you can also see that the second row and third row are actually in a nice multiple. But to make it slightly easier to see it, let's simplify a little bit. So what I'm going to do now is to make it, it's not necessary step, but you can see that I'm just going to make it looks nicer, so it doesn't look so ugly. Okay, so I'm going to divide minus 3 on the second row and do the same thing, divide by minus 5 on third row. Let me have a space here. Okay, and do it the same thing here. So divide by minus 4. Okay. So now once I have this, then I can actually easily take this 1 and eliminate the 1 here. So that's essentially why I want to do all these things, so I can see it more easily. But as you can see that you don't have to, right? Because if you directly take this -3 and then cancel out -5, that also works. It's just the number looks a little bit ugly. Okay, so now I'm going to take row 2 times -1 added to row 3. Okay, so keep this. Okay, I know the number looks a little bit ugly, but this is just like because it's hard to design a very perfect question like this. So let me just give you the final number here. You can definitely calculate and confirm yourself. Okay, so you can see that because it's 1313 here, right? So it actually completely cancel out. Okay, so now I want to pause here a little bit and ask everyone to stare at this system, this REF. Can anyone tell me, is this system always solvable for any arbitrary A, B, and C? Can anyone want to answer using microphone or chat? No. Okay, someone say no. Okay. Any other answer? Is this system always solvable for any arbitrary A, B, and C? Okay, if the answer is no, then tell me when it's not solvable. When it's not going to be solvable. Right, this one, anyone want to guess? Because you say no, right? So in what case that it's not going to be solvable?
When 5b plus 2a minus 3c doesn't equal 0?
Yeah. So basically you can see, so I cannot see who actually is talking. I only have one screen. But if you see that the reason that it's not always solvable, because now you have everything on the left-hand side 0, 0, 0, right? So there's some bad case might happen, right? The bad situation might happen is that if the right-hand side is not equal to 0, right? If this thing is not equal to 0, then we are going to have a contradiction, right? Then it will become 0C1 plus 0C2 plus 0C3 equals something non-zero. And this is exactly the inconsistent situation that we want to avoid, right? So you can see that in this case, you know that the system will be inconsistent, meaning not solvable, if the right-hand side is not 0, right? And which is possible. I want to make a remark, right? Which is possible. You can actually easily pick some number, right? So what does this mean? It means that we are actually in an unlucky situation, right? If you pick unlucky choices of A, B, and C, then the system is not solvable, meaning there are some choices of A, B, and C would not be able to be represented as a linear combination of these 3 vectors. That means when you take a collection of all linear combination of these 3 vectors, U1, U2, and U3, you're going to miss a lot of actually certain vectors in R3, right? You didn't hit all the vector, you actually missed some of them. So that means it's bad in the sense that then it's not going to be, so basically it means that for some vector, A, B, and C in R3, right? It cannot be a linear combination. Oops, sorry. Linear combination of U1 and U2 and U3. So you miss some of them, right? So in this case, we say that, okay, then we get the conclusion that we cannot say it's a spanning set. So it's not a spanning set for the whole R3 because you're going to miss some of the vectors. Okay, so you can see that's why this type of problem is conceptual in the sense that first you need to turn this question into solving a 3x3 system, right? And the algebra, I believe, is not too bad. But once you reach to the end, you need to see that, okay, what does that mean, right? Is this system always solvable, right? So you want to so this type of question is conceptual, right? In my opinion, this is getting harder. That's why after today's class, you should definitely review my notes and then also read the textbook because the textbook will give you more systematic knowledge here. And also sometimes I will try to avoid covering the exact same examples in the textbook. So you should also read the textbook because their example may be different than mine. I intentionally do this so you can see more example. So I assume people will always read the textbook afterwards. So then they will see one set of example and I put different kind of example. So you will see more, okay? So now let's see. So now this last example for the, I think it's the last example for the spanning set is going to be even more conceptual in the sense that I'm going to use a very general vector space, okay? And in my opinion, from the past experience, people always have hard time dealing with this type of general vector space because it's hard to kind of work with it in the sense that it's not obvious or not like, you may not be familiar with it. So if it's R3, some vector in R3, you can easily write down A, B, and C and all that. But if we're talking about, for example, a vector space like a polynomial space, then there's some trick you need to do. Okay, so first of all, I'm going to use this specific polynomial space as my abstract vector space. So let's recall what's the definition of Pn, right? Remember we talked about this in 3.1 like earlier. So the vector space Pn, in this case, I'm going to pick P3. P3 is the collection of all the polynomials of degree up to 2, including 2, right? So a typical example, so you're collecting a whole bunch of polynomials. What's a polynomial looks like? It looks like something like this. So this polynomial P of X is a function, but it looks like some constant A plus some constant B times X, some constant C times X squared. And A, B, C can be any number. So for example, you could possibly have just the constant A, or you can have, say, X plus 3x squared, right? Or for example, 3 minus 5x squared. All type of thing is collected in this vector space P3. Any polynomial of degree at most 2, then it's going to be collected in this vector space. Okay. So now the question is, how are we going to find a spanning set for P3? Or if you give me some choices of 3 polynomial or 2, right? Is it going to be a spanning set, right? So, but first I want to make this nice observation that there's a standard 3 vectors, which is going to span P3. Definitely, no doubt, okay? So these 3 vectors are actually 1, x, and x squared. So you can see that even though it's a function, right, a polynomial, but I called it vector because it's an element in the vector space. So sometimes if you read the textbook or some other literature, you will see that they call something vector, even though it doesn't look like the traditional vector we saw. But what they meant is that it's an element in a vector space. So I can still call it a vector in the general sense. So you can see that this 3 vector, or you can say the 3 elements, 1, x, and x squared, is going to span the whole P3. Okay, so you can write it down in this way. Span of 1 x squared is P3. So how do I convince myself that this is the case, right? So in other words, you're telling me all the polynomial of degree at most 2 should be written as a linear combination of 1, x, and x squared, right? But as you can imagine, then you can see that any polynomial of degree at most 2 is going to look like exactly like this P here, right? So that's called it like this, right? But you can see that when we write it down like this is already a linear combination format, right? It looks like really A times 1 plus B times X plus C times X squared, right? So basically any polynomial, any element in this vector space P3 is definitely going to look like a linear combination of 1, x, and x squared, right? Because how we form it, right? So basically, this is later on, you're going to see that these 3 polynomial, 3 vector here is essentially our standard foundation for the P3. Okay, So we already know we can definitely find some set which span the whole P3. But of course, as you can imagine, these three vectors, 1x and x squared, are not really interesting. They're too trivial or too standard. So we want to work with some a little bit more complicated vectors, right? But at least we already know this three is going to span P3. Okay, so let's see this example. So again, same idea, right? So I have three vectors, okay? So I'm asking, is this three vectors 1 minus x squared, x plus 2, and x squared? So if I call it three vectors, that means call it P1x, right? And the second vector, P2x, and third one, x squared. It's these three elements, three vectors are going to span the whole P3, right? I'm again asking the same question, right? So what I'm asking is it possible for any arbitrary polynomial, right? Or you can say vector in P3, is any arbitrary polynomial going to be a linear combination of these three, P1, P2, and P3, right? So we're asking the same question over and over again, but now I'm dealing with different type of vector space, right? So we want to be able to work with something more abstract. So basically you can see that then the idea is I'm going to check whether any polynomial in P3 is going to be a linear combination of these three polynomial or not. And mathematically, it's equivalent to ask whether we can always solve or find C1, C2, or C3 such that this arbitrary polynomial, right, if you call it P of x, right, it's going to be equal to a linear combination of P1 plus C2 times P2 plus C3 times x squared, right? So you can see that this is essentially, you're giving me an arbitrary polynomial of degree at most 2, right? C can be 0. That's why I say it degree at most 2. It could be less. Is left-hand side always can be solved as a linear combination of C1, P1 times C2, P2 times C3, P3, right? So I'm solving the same problem, but now instead of the traditional vector, I'm working with the polynomial here. That's why it's slightly harder. So now the thing is that if you look at this, it's not obvious what system we want to solve because there's all this like x going around, right? So in order to turn this into a more obvious format of the system, for polynomial especially, you need to do this trick. So what I'm going to do is I'm going to rebundle all the terms on the right-hand side. So you can see that the left-hand side, you have things nicely arranged into constant and something involve x, something involve x squared. But right-hand side is kind of mixed, right? So I'm going to rearrange it, okay? So I'm going to rearrange it to the following. So I pick out all the constant term here, right? So you can see that I'm going to just expand everything, but put all the constant together and do the same thing with the x term. But I think we only have one x term. So this is C2 times x. And for the x squared, I have something looks like minus C1 plus C3, right, x squared. I'm just going to rewrite it. So now you can see that after I rewrite it, then it looks nicer, right? It really looks like constant plus something involving x and something involving x squared. So the reason I'm going to do that is the following, right? So we know we want to this P of x equals right-hand side, right? We want to see whether we can solve it. But when we say two functions are equal to each other, what we really meant is it should be equal for all x, right? So this equal sign is for all x. It should be true disregard which value of x you plug in, right? So for example, if you think of that in calculus, right, when we say, oh, there's a function equal f of x equals g of x, what we really meant, if you say these two functions are equal, it means that it should be equal whatever the value of x you plug in, right? So it should be equal everywhere. So basically same thing for polynomial, right? When you say two polynomials are equal, what you really meant is that it's equal at all possible value of x. But there's a trick that if you want this to be true, the only possibility is for all the corresponding coefficient to be equal. Okay, so let me first write down what I said here. So for two polynomial to be equal, all corresponding coefficients are equal. So what does that mean? It means if you compare left-hand side and right-hand side, right? So we have the constant term a on the left-hand side. And then this a should be the same as this constant on the right-hand side. And then I also have b, which is the coefficient for x on the left-hand side. Then it should be equal to the corresponding coefficient on the right. That's why you can see this is exactly why I need to rebundle or rewrite the right-hand side. And then also the c here should be also equal to the right-hand side here. Okay, so this is how we're able to write down the system here. So then basically what you're solving is, okay, first you want to essentially, this is the same as solving the following, right? Then you are going to have C1 plus 2C2 equals A. And C2 is going to equal B. And you can see that minus C1 plus C3 is going to be C. That's how we write down the system here, right? So basically I'm equating the corresponding coefficient, right? So this C1 plus 2C2 equals A, C2 equals B, and this whole new thing equals C. Okay, so that's essentially how we convert the thing we want to solve into a 3x3 system, right? So you can see that it's, if you want to use it as an arithmetic matrix, right, then this becomes 1, 2, 0, right? If your variable is C1, C2, and C3, and right-hand side is A, B, and C, and we have C2 here, minus 1, 0, and 1. So this is the same thing, right? The same system. If you want to use arithmetic matrix to solve it, right? So, okay, so now that's C. So how are we going to solve this thing, right? So first of all, because the problem I pick here, I think either you use arithmetic matrix or directly solve it from this original system. I think either one would be the same. But you can already observe that from the second equation, we already know C2, this coefficient C2 has to be B. So we can start from here, right? So we already know this is too easy in the sense that like the system is not complicated enough. So I'm stick with this original way. So we already know C2 equals B. Okay. Then we can plug in back to C1. Right, then C1 is A minus minus 2C2, which is A minus 2B. Okay. If you're not comfortable of C1, C2, and C3, put it as X1, X2, and X3. Probably that's feel a little bit better because then you won't confuse with A, B, and C. And then now once you solve that, then plugging back to the third equation, then C3 is C plus C1, which means C1 is A minus 2B, right? So actually, I don't need to simplify. This is okay. So what does that mean? Now you can see that this is almost the same as the first problem when we solve spanning set for the R3, right? Because you can see now all the coefficient really depends on the A, B, and C you choose. If you observe the pattern, you probably already noticed that a polynomial like this actually has a similarity to a vector in R3, right? So I said, oh, you can pick any arbitrary polynomial, a plus bx plus cx squared. If you think about it, all you really care is kind of just the a, b, and c, right? So in some sense, you can identify a polynomial like that with a vector in R3, right? That's why you can see that when it comes to solving the augmented matrix, it looks the same, right? If you take out all the polynomial stuff, right? If you just look at the coefficient, it's as if we were solving a system in R3, right? If you think about it, you can see that the system here is similar to what we've done before, right? But of course, for polynomial, you need to first take out essentially manage to write down the correct augmented matrix or the system. So now we solve C2 equals B, and C3, which is your X3, if you want to call it X3, and also C1 to be A minus 2B. So that's double check, right? So basically we know that any polynomial, A plus BX plus CX squared can be written as linear combination of those three polynomial we start with, the P1, P2, and P3, right? Okay, so it's 1 minus x squared to start with. Oops, sorry. So first coefficient is C1. So C1 is A minus 2B. So this would pair with the P1. Okay, plus C2, which is B, paired with P2. P2 is x plus 2, right? And then plus C3, a little bit ugly, times P3, which is x squared. So you can actually, this is the part you can check. This is where you check your solution, right? So you can see that it doesn't matter what polynomial you give to me from P3, it actually always can be written as a linear combination of the first vector, second, and the third one, right? So this is in a linear combination. So that's why you can say that indeed, these three vectors, if you call it vectors, these three polynomials span the whole P3. Because any polynomial here on the left-hand side can be written as a linear combination of those three, okay? So this is by far, I would say, the most difficult example here. It doesn't mean that algebra is difficult. It just means that because there's a small gap here, you need to turn it into a small transition. You need to turn solving a linear combination of polynomials into something that we are familiar with. And you need to be able to find the coefficient in terms of A, B, and C. So you really, really have to go back and redo the problem yourself. Just by watching me, it's not going to just by watching me doing this, it looks easy or it makes sense. But if I throw you different example, right, can you react? Can you really do it yourself? So if I haven't emphasized enough, then I should say it again, that each time after you come to the Zoom class, you definitely also need to go back to read the textbook and then read my notes, right? Just by sitting in the class, like you will see something, but you're not going to fully understand, right? So if all you did was coming to sitting in the Zoom class and then do some homework and be done with it, this is not going to be enough. Okay, you need to actually proactively to go over the lecture notes again and also do enough example for this type of problem, especially from now on, things getting much more difficult. Okay, so before we end the 3.2, there's one last one last topic that I want to do. Okay, so I noticed that it's at 1:45 almost now. So as I said, I'm going to go 10 minutes further because I started late. So for anyone who actually need to leave, that's fine. You're free to leave if you have anything. If you can stay, that will be even better. But I'm going to continue until 1:55, and then I will put it in the recording. So if you miss the last 10 minutes, you can still see it later on. Yeah, I think it's better to keep it full 75 minutes. So like for the completeness. Okay, so the last thing I want to talk about is the relationship between the null space that we discussed earlier and solving a system, there's actually a significant relationship between knowing what the null space looks like and what the solution of the system looks like, or essentially how many solutions are there. Okay, so again, null space is the collection of all x such that ax equals 0. So you're collecting all the solution to the homogeneous system, right? How does this relate to the solution set of a general system ax equals b? So it turns out that this following theorem tells us that if you start with a system ax equals b, doesn't matter what b is. If you already know, right, this is the assumption. If you already know this system is consistent, so I need to know it's consistent to start with. If it's consistent, and then if you already know, okay, it's consistent means it has at least one solution, right? It might have infinite many, we don't know, but at least it's consistent. So at least we can find a solution. So if x naught, x0 is a particular solution solving this system, one of them, right? Then I want to see that what's the relation between this solution and all the other solution. It turns out that if you have a vector y is another solution to the same system, then if and only if means that it's equivalent to say that then we know that this second solution or all the other possible solution is going to look like this x0 that we know of plus another vector z. And this z essentially is any vector in the null space. So what does that mean? That means, okay, if I already know the system is consistent, so I already know there's one solution x0 to start with. It turns out that if I have more than one solution, then any other solution y is going to look like my original solution x0 plus some vector from the null space. So what does this tell you? This essentially tells you if you know, in this case, if the system is already consistent, if you know how many vectors are there in the null space, then it corresponding to how many solutions for ax equals b, right? Because you can see that if your null space has infinite many vector z possible choices, right? Then you can always add it to x0 to form another solution y, right? So basically in this case, knowing the size of null space is the same as knowing the solution set for my ax equals b. And this is actually the significance relation between the null space and my solution set. In other words, and actually the reason why we have this phenomena is because the system is linear. Okay, and if you still recall, if you took a differential equation class before, if you remember that when you're trying to solve the general solution of some differential equation, remember you always find the solution that equals 0 first, right? And add up to the particular solution, right? Then that will give you the most general solution, right? It's exactly the same because your differential equation is also linear. Okay, so you can see that they're the same thing. The phenomena is the same. So I want to briefly prove this thing to show you that or convince you this is the case, right? So how do I convince you that any other solution y can be written as some solution plus a null space vector, right? So the only thing I need to show is that I want to show you the difference of two solutions. I want to show you if you take y minus x0, I want to show you this vector should lies in the null space, right? Because then y minus x0 is going to be z. If this is the case, then I'm done, right? So I want to show you the difference of two solutions to the system, general system ax equals b should be a vector in null space. Then so essentially I'm saying y minus x0 is indeed equal to some vector z in a null space. Then we can rewrite it as y equals x0 plus z, right? So this is actually not hard to prove, and it's really because the system ax equals b is linear. Okay, so it's actually two lines proof. So we say if okay, so assume x0 already solved the system, right? And there's another solution also solve the same system, right? So x0 will satisfy a times x0 equals b, and y also satisfy ay equals b. Now we want to see that what would be this difference vector looks like, right? So we take a times the difference, if you code it z, right? Then, because you know that when you do the subtraction and you multiply a matrix, because essentially this matrix is linear, so you can actually separate into two things, right? Ay minus a x0. But we already know to start with, we assume x0 and y are both solving the same system, so they are both equal to b. So once you subtract it, it's going to be 0. So what does that mean? It means y minus x0 really satisfy a times that equals 0, meaning it's actually in the null space. So in other words, if you have two solutions like this, then the difference is going to be in null space. Or you can say they only differ by a vector from the null space. So in a very special case, right, then you can see that what if your null space is trivial? It's possible, right? So as I said, null space definitely always has a solution, right? Which is the trivial solution, 0, 0, 0 vector. But it could have more, right? So it's either 0 vector itself, only 0 vector, or you could have infinite many vector, right? So we want to see that in this setting, right? In this situation, what does that mean to have null space to be trivial, right? So if, again, we use the same thing, we say, okay, if I already know this system is consistent, and if I know my null space is trivial, meaning there's only one solution, the unique trivial solution, then what does that tell us about the solution set of ax equals b? Then it actually tells us that it's only going to have one unique solution. Here, A is actually a general m by n matrix, right? It does not necessarily need to be non-singular or anything, right? Because it may not make sense to talk about invertibility or not, right? So this is another criterion for having a unique solution, right? You can think about it, because if you tell me that any other solution is going to be the first one plus some vector from null space, but I tell you that now null space only has 0, can only be 0, right? Then you already right away know that y has to be equal to x0. There's no other possibility, right? So basically you can see that then indeed, but you want to be careful, right? We need to start with by assuming this system is consistent, right? We need to have this x0 to start with, right? If we don't know whether the system is consistent or not, then you cannot use this theorem, right? Because it's possible that you have a space as a matrix or system where the null space has a lot of things, but your system may not be solvable, right? Then you need to be careful. Then in this case, you cannot use this theorem. So that's why I emphasize that for this theorem, you need to start with assuming that you already know it's consistent, or at least you need to have some evidence showing that it's consistent. Otherwise, you cannot use this theorem or this relation. But if you know it's already consistent, then there's a phenomena that any two solution, the difference is going to be a vector in the null space. Okay, so I think we have enough conceptual thing today. So next Tuesday coming back, I'm going to start 3.3, and for next week, the whole thing will be 3.3 and 3.4. So if you already catch up to this far, I would say that please, for your own benefit, that you should read in advance for 3.3, at least for 3.3, for example, so you know what's going on. So for 3.3, what we're going to discuss is that how to find an economical spanning set, right? So for now, we know that if you give me like a set of vectors, I can check whether it can span the whole thing. But we didn't discuss that whether these choices of the set is the most economical or not, right? You might actually choose too many of them, which is a little bit redundant, right? So on 3.3, section 3.3, what we're going to discuss is about when this spanning set is minimal, right? So which means that you can actually span the whole space, but at the same time, keep the amount of vectors to be the minimum, okay? And later on, you're going to see that if this is the case, then we are going to find a nice, what we call something called basis. Okay, so so thanks for staying late. I know that there's still some people here. So if you have any question, feel free to stay. Otherwise, you're good to go. Thank you for staying with me today.
Actually, I wanted to ask about the last two problems on the homework
Yeah, sure. So,
because I kind of got lost in what it's actually asking me to do.
okay, sure. Give me a second. Let me pull out the textbook. So last two, you mean 10 and 11?
Yeah.
Okay. Okay, so so for 10 and 11, let me see. So okay, so first of all, for 10, which a felt okay. So they already tell you that for example, number 10, they already tell you with this new addition defined, this new vector space, sorry, actually this new space is not a vector space, right? So if it's not, then that means among all the axioms that we discussed for vector space, right? The two of them are closure and also the other 8, which is A1 to A8, right? So some of them fail, right? So what they ask is that you need to essentially check through all these axioms and to exactly say that which of them are actually failed.
So do I just have to make up examples to disprove them?
No, you can do that, or you can actually generally prove it. There's so many ways to do it. So let's do number 10 together. So let me share my screen with you so I can actually write something down. Give me a second. Okay, so now let's see, right? So okay, so let me. If you have the textbook, then we can actually check through all the axiom here. So first of all, so if you they call it S, right? So this is the set, and X is essentially all the possible numbers in R2, right? Essentially, it's a collection of all the pair of number. So essentially, you can think of that it collects the same thing as all the points in R2, right? But the difference between this set with R2 is that now the addition is new, right? So then, yeah, you can actually either pick a counter example to disprove something, right? If you want to say, for example, A5, or I don't know, I don't remember which one failed. I'm just making up example. Let's say if A6 fails, right? You can either show me that directly, generally, it will not hold, or you can actually pick a counter example. That also works as well, right? As long as you can show that it's not always correct, then you're fine, right? So then the addition here, so the scalar multiplication is the same. If you take alpha times a pair of number, it's going to be what we know of, right? But here the addition is different, right? So that's why they use this new notation. They want to distinguish from the original addition, and it's a very weird addition. So essentially, you only add up the first two number and then first coordinate, and the second one becomes 0. Okay, so first let's see. Let's check, right? So for closure, right? What does closure mean? Closure means that if you have random two vectors from this, two elements from this set, right? Random two pair. When you add them up, will it still be in this set, right? So let's see. So if I call this random two vector, I just call it x1, x2, and y1, y2, right? If I add them up using the new addition, right? We already know it's going to be like this, right?
Yeah.
Does this in S it will still be, right? Because S has no restriction, right? Because S, what's the definition of S? Is the set of all the pairs of real numbers, right? So as you can see that there's pretty much no restriction for S. That's why if you add up two vectors, or even more, if you want to do the scalar multiplication, it will still be in S. So the closure is kind of silly that the closure definitely hold, because you add up two pair of numbers, it will still be a pair of numbers, right? So it really, in this case, the closure definitely holds. So the problem is naturally not on the closure, okay? So, but you need to still check, right? You need to show me that indeed that the closure are satisfied, right? Then we move on to A1, right? So let's see. A1 says if you add up two vectors, say x plus y, arbitrary vectors, it has to be equal to the reverse order y plus x. Is this true?
It should still be true.
It should be true, right? But you need to write it down, right? So for example, let's just make sure that we are on the same picture. So you say, okay, start with x plus y, right? And this will be x1 plus y1 and 0, right? And you can say that, okay, then what about y plus x? In this case, when you check through the definition for vector space axioms, you need to be careful, like they only use plus there, but what they meant is the addition, whatever we define. So that's why in this case, I use this new addition here. So if you do this, you can see that y plus x will be this, but since you're just adding up two numbers, so the first coordinate will be equal. Yeah, so this two will definitely be equal. So A1 holds, right? Like what you said. So you really need to check through all the things here. So now the question is, actually, I can see A3 may have quite problems, right? So, okay, so do you agree that A3 have issue? Like A3, like
Yeah, x plus 0 equals x.
Yeah, so you can see, right? Like you can actually find me a, either you can directly prove it, like using, like just like write down the left-hand side and write down the right-hand side and show them that it's possible that they may not equal, right? Or you can actually find me a counter example, right? So let me show you the most general way, because the most general way is usually the hardest one. So let's see. So if you have some vector, right? So essentially, I want to show that there's no way such zero element exists. There's no way. Okay. So I'm saying that, okay, if I have some vector that's the potential candidate for zero vector, right? So let me call it U, okay? This is the candidate for zero vector. And let's see if is it possible that add this to x and it will still be x, right? And let me code it U to be U1, U2, okay? But then you will see that and then x will still be x1, x2, but you will see that U1, U plus x will be U1 plus x1, and the second one will be 0, right? Because this is the new addition. So what does that tells you? It tells you that essentially, if you call x to be x1, x2, right? If x2 is not 0, then this may not be equal to x, right? Did you see it?
Yeah.
Right? So U1 could be 0, right? But even you choose U2 to be 0, then this may not be equal if x2 is not 0. So either you can tell me, showing me like this, or you can just give me a candidate. You can say, okay, I pick some random vector, right? And you say, by our weird defined addition, there's no way I can find a vector such that this vector at x will be x, right? You can easily see, right? There's no way you can find some other vector such that once you add it to x, it will be x itself, right? Because when you do the weird addition, it always forces the second coordinate to be 0, right? So either way is fine. You just need to show me that, yeah, this axiom A3 is not generally true for all the possible x. That's why it fails. Does that make sense?
Yeah, but this is what confused me, because we have like the weird addition, But it says S includes every coordinate pair. So wouldn't the addition automatically fail as well if you add two vectors that don't have a secondary value of 0 together?
What do you mean? Like, what do you mean? Say again? Like,
Say we make up like a thing like 2, 1, and then I don't know, like 3, 2. If you add those together, 1 plus 2 isn't 0. So that's why I got confused. Like,
okay. So in this case, right, when you add up in this addition, when you add up these two, right, this would be under our newly defined definition. If you add up 2, 1 and 3, 2, not the usual sense we know of, because here we are working with a weird space where we change the addition. We can always define whatever the addition we like, right? Because addition is a operation that we can define it ourselves, right? It's like I want to call this person John. I can call the other person Jimmy, right? I mean, name, you can pick a name yourself, right? So we can pick the addition by ourselves. So in this newly defined addition, if you add up these two, it's going to be 5, 0. So, but then this is a little bit different than the A3, right? Because A3 was asking, is it possible to find a vector such that this vector add any other vector x is going to be x itself? So I'm not 100% sure that whether I see the connection between your question and A3 in particular.
Yeah, it just threw me off because I get we are literally just changing the rules specifically.
Okay. Exactly. Yeah, we changed the rule completely. So you should abandon all the addition that you know of back then. They're just saying that, okay, because we are free to choose however we define the scalar multiplication and addition, right? So in the usual case, if we have the usual R2, we collect a pair of number and we do the usual scalar multiplication and addition that we know of, the traditional one. That's giving us a vector space for sure, because we know R2 with the usual definition is vector space. Now what they say is that, okay, let's stick with the same set of numbers, right? Let's stick with a pair of numbers. But then I change the operation, the addition. Then you can see that it will no longer be a vector space anymore. So this example essentially tells us that a vector space, to qualify as a vector space, not only it relates to what's the collection of the element it is, it also highly depends on what's the addition and the scalar multiplication that you define. If you pick a bad choice or define a bad operation, then it will make the same thing not a vector space anymore. So that's what they're doing in 10 and 11 exactly. Well, you can see in 11, this time they changed the scalar multiplication instead. So you can see that in this case, A3 is going to fail because once you do add up two things together, it will force the second coordinate to be 0. So which this tells you that it doesn't matter which vector you pick. If you add to another vector x, it will always push the second coordinate to be 0. So this will not in general equal to x anymore. So which means that there's no way you can find a successful 0 element to make it work, to satisfy the definition of 0 element. So which tells you in this setting, 0 element does not exist because we poorly define our addition. Does that make sense now?
Okay. Yeah, I'm starting to get it more.
This is you want to think about the logic. It's actually quite like, this is not easy. Actually, I just got this question yesterday.